All right, hey everyone. Welcome back to my Computational Methods Homework 2 series. So in part A of then part 2, we explain and code the secant and Newton methods for finding the root of a scalar 1D function. And now we're going to explain and implement the Newton's method for finding the root of a vector function. So of n dimensions, right? Excuse me. Um, And so this is actually not too bad, especially because we wrote a Newton's method function last time, right? Except instead of taking a function like of just one point and like a one-dimensional function, it's going to take in a vector, right? So the first thing is we're going to have to write, just like how we wrote our function last time, we're going to have to write a vector, right? So we're going to say it comes in a vector. So we're imagining like a point x, y, z, right? So it's going to be, we're going to unwrap it. Let's say it's three dimensions, right? Really, what you could do is like take the size of the vector. If you wanted this to be dynamic, you would take the vector size and assign that many variables based on the side. But here we'll assume it's three dimensions. So x, y, z just equals the vector. And then we're going to apply the functions. So return jnp.array, and I'm just going to pick random functions for my x, y, and z, right? So I'm going to say one of our functions is x minus 5 times x plus 6. That's going to be one that I can count on to know. I'm going to say the second function is y 5y squared plus 2y plus times y plus 7. I don't even actually know if that one has 0, so that should be fun. And then my third one shouldn't have a bracket yet. For z is going to be 5 plus np dot jnp, sorry, jnp dot sine of z. There you go. So we have our three functions for array, for our vector, and then now we're going to have to just modify our Newton's method for one dimension for three dimensions, right? So it's going to take in the same values, right? And so the first thing is x naught used to be a point. But now, if you think about it, it's being computed as a vector. So we want it, or an array. So we want it to um, at least have one dimension, right? And so we've used this before, but jnp dot at least 1d um, x naught. There we go. And then it's not enough for us to use the gradient this time. Because we're in three dimensions, what is um, a bigger... Why is this having a... I mean, it's good. Looks good to me. Because we'll find out when we run it. So the three-dimensional version of gradient is the Jacobian, right? So we want to run the Jacobian of f. And then we iterate, we compute, but we can't do division, right, with matrices. We just can't do it. The way you have to do it is just multiply by the inverse, right? So we're going to take the inverse of our Jacobian, so JNP dot linear algebra dot inverse of the Jacobian, so df, and then we're going to multiply it by our f naught matrix, right? So that's the same thing as f naught divided by um, shouldn't this be maybe df naught, I guess, right? Because it has to be at that point. Um, and then so that's the same thing as what we were doing before. And then for our tolerance, right, instead of taking the absolute value, because it's a vector, right, we're going to normalize that vector. We're going to make it the unit vector. So linear algebra dot norm, wait, no, if jnp dot linear alg dot it's tough dot norm, typing's a little rough, yeah, um, of f1 is less than the tolerance, Then the root successfully found, and then you can break, and then x naught equals f naught, and then we update it the same thing that happens before, right? And then so let's go ahead and try this, right? So let's just call of Newton of f2, and then my guess is gonna be like 51, 4, and 5, not 5, because that's the actual one, 7. And let's do this. Invalid syntax. Should be fine. Okay, yeah, it should be. So I'm guessing here what's going on is that 5 plus j and p sine z couldn't be found. Yeah, it doesn't have a root. Exactly. That makes complete sense. That 573.3566, I guess we didn't code that super well. I mean, super elegantly, but it's the point. It's just that's how many iterations. I mean, that's how much we tried to get to the value. But if you think about 5 plus sine, it's just sine shifted upwards, so it never hits 0, right? And so it properly prints out the root cannot be found. And if to make this better, and you can try this at home, you can make it so it'll tell you exactly which roots could not be found, like the x root, the y root, the z root, the so on and so forth. But this is a very, very simple way to use Newton's method on a vector to calculate the zeros. Thanks, and see you guys in the next part.